the stage to Julio Freidman, that coming from Columbia University.
Thank you very much. I'm really delighted to be here. Me alegra mucho asistir a este simposio. We are in the industrial building. Estamos en el edificio industrial. I'm delighted to be able to talk about this subject here. Thank you so much for having me. I'm going to be the guy who tells you all the bad news. So let's start with the fact that I wanted to focus a couple of years ago on heat. I wanted to focus on industrial heat because I heard some idiots saying that we can electrify everything, and I said, I know that's not true, so what can we do? And so I said, let's go after heat. Heat's hard. Heat's a hard thing to do. Most of the industrial processes, including the industrial processes up here, start by melting a rock. If you melt a rock, you need heat. So what can you do? And it turns out that just the heat-related emissions from heavy industry are more than all the cars and planes in the world. Yes, you never thought of it that way. All the heat from heavy industry is more than all the cars and planes in the world, and I dare say we've spent a little more time thinking about cars and planes than we have about industrial heat. So the question is, what can you do? We can admire the problem, or we can try to do something, and so we started getting into this, and we realized a couple of things. First of all, heavy industry is not the industrial sector. A lot of people who enter the decarbonization standpoint think about it from the perspective of power, because they've spent their lives working on decarbonizing power, which is a good and important and virtuous thing to do. They're not the same. Most commodities are consumed globally, not locally. So a very small change in price completely affects market shares. Most of these companies are also working with assets that are extremely long-lived, as we heard earlier, and are also very expensive to replace. In addition, these are generally considered essential national industries. The steel industry in South Korea is not just something they do. It is a huge part of their economy. And most people don't see it. Most people see power, most people see cars, most people see planes and fuels. Most people don't go to the store and buy 10,000 tons of concrete. So the question is, how do you get this in people's eyes and minds? It's a hard challenge. The really bad news is we do not have a lot of options, and the people up here have mentioned that, and they're working on good options, and I'm delighted to see it. But we don't have a lot of options, and we need better and more. And what we found most daunting as we started all of this work was that there was no data. There was no data. You couldn't go out and find it. Nobody goes out and buys heat, and they don't recognize it in the industrial settings, like everything's set forward in tons or kilowatts. They're not gigajoules. So it was really hard to start working on this project. The good news, though, is that we have good news. First, some more bad news. The most important thing about heavy industry is the high temperatures required. This is what makes it so hard to electrify, and it makes it so hard to deposit the heat in the reactors. So steel starts at 1,200 degrees Celsius. Cement is 1,450 Celsius. There are not a lot of options to do that. Biomass can do it with biogas. That can hit that temperature. Electrical resistance heating actually can reach that temperature. You just can't put the heat in the reactor. So that's a problem. Hydrogen can do it. Nuclear can't. Nuclear is not hot enough. So that's a pretty small deck. There's not that many things you can do. So we sent out to do a big techno-economic analysis. Please come to our website and download the report. These are the punchlines. I've gone through the first ones today, and I'll sort of unpack the later ones as we go. One of the things to recognize, and this has already been said, is actually when you look at the comparison of options for deep decarbonization, carbon capture and storage ends up being important. It ends up being the thing you have to do. If you want to get deep emissions, that's one of the things. Okay, well, we can do that. Also, low-carbon hydrogen ends up being really important. We saw that already with Martin Pei's presentation. It's one of the things that we saw from Alberto Aragonés' presentation. Low-carbon hydrogen is important. There's lots of ways to get it. That's fine. In all cases, we're going to need better policies. The markets can't deliver this today. We just need a new set of policies that can protect domestic industries or provide large enough incentives to finance, do whatever it is we need to do. So, we had not seen anything like this before, so we made it. Basically, blue ones are low carbon footprint, red ones are not so low carbon footprint, and we just put it up in cost per gigajoule. This is everything. These are all the options. And basically, This line here, the first line is US price of gas, and that line is European price of gas. So the first thing you should see is all the options cost a lot more than gas. That makes it hard. Okay. Another thing you can find is that many of the options need CCS. For example, low carbon hydrogen, the cheap option in most markets is CCS. And the reason why that's true is because most places do not have cheap low carbon power. Sweden is an exception. Sweden does have cheap low carbon power. America does not. China does not. So that makes it hard to use there. And even things that you think would be straightforward, like biodiesel or hydropower making hydrogen and stuff, like most markets, it just doesn't work. So the good news is that this is something we actually can and do know how to do. So this is the carbon footprint for power in the United States. And this is actually, I'm sorry, not the carbon footprint. I pulled the carbon footprint slide. It's terrible. It's not even worth looking at. This is the cost. So this is what the cost for a firm industrial power contract looks like in the US. This is not a 3-cent per kilowatt hour solar panel in Chile. This is what the actual industrial firm power price is. So when you want power, 90% capacity factor, 24 hours a day, that's the price you pay, basically $50 to $120 a megawatt hour with a median price close to 70. So that's quite expensive, actually. And we are not close to having zero carbon, firm, cheap power yet. So we need to work on that too. Lots of good people are working on that, we know it. But until we have this, electrification remains a challenge because it's not cheap or carbon free. So let's talk about hydrogen. I'm a big fan of hydrogen. We make hydrogen today at enormous scales. It's a globally used commodity, and it's pretty cheap. Cost of making hydrogen today is about $1.20 a kilogram, and that's good. That, for the record, is more than the cost of natural gas by quite a bit, but we know how to make it at enormous volumes. We also vent the CO2 from steam methane reformers today. That all goes up into the air and oceans, and that's bad. If you wanted to capture that carbon, what we call blue hydrogen, you can do that today. It adds about 20% to the cost. That's more than people want to pay, but it's not like a huge amount of money. We would know how to do that. You can't do it everywhere, but you can do it in most industrial ports. You can do it in Rotterdam, you can do it in Texas, you can do it in Tianjin, you can do it in Teesside and Aberdeen. Like, there's places you can do it today because we have the storage. If you tried to do the same thing with renewable power, in US markets, it's really unattractive, and in most markets, it's not going to pan out. It's a factor of 4. In many markets, it's a factor of 10 more expensive. But that's okay. Green hydrogen is getting cheaper. The cost of electrolyzers is dropping. The cost of green power is dropping. Eventually, green power will be firm, and the cost will be cheap enough to move into the business. And I look forward to that day. So we can start with blue hydrogen now, make hydrogen with no carbon emissions, and then as green hydrogen becomes increasingly cheaper, we can just bring it into the market as an on-ramp and make hydrogen go from blue to turquoise to green over time. We also just wanted to say, well, we've talked about these things in dollars per gigajoule, but nobody goes out and buys gigajoules either. They buy steel. So what do these things look like for real? And so we put in here just prices. If we took various kinds of heat, electrical resistance heating from the grid in the United States or from the grid in Europe, or if you use biomass, use really good blue hydrogen or not so good blue hydrogen, use renewable hydrogen, or if you just did CCS on just the heat, or if you did CCS on the full plant and got the process emissions too. You're just like, what does it do to the price of the commodity? Because that's what people really want to know. How much more do we pay? So this is for clinker, and this is the price for 25% increase, 50% increase, 100% price increase. And that line there is $8 gas, which is, Asia price or something like that. Okay? So most of these options more than double the price of production wholesale concrete. More than double the wholesale price. That's what the deal is. Interesting fact, though, it does not double the price of the product. It doubles the price wholesale, but not the finished good. So for example, if you built a bridge out of concrete, bridge is mostly concrete, price of the bridge goes up 1% if you double the cost of concrete. This means that government procurement is a very strong policy option because the government buys 50% of the concrete of the world. They could add this. Most of the cost of a bridge is labor and time and land and design and all these other kinds of things. Same thing's true for steel. Hello? Same thing's true for steel. Steel's not so bad, but steel's more expensive. Steel's $300 a ton. So that's the price for European gas, 25, 50, 100% price increase. Again, the cheap options, CCS on hydrogen, great. And it basically adds quite a bit to the price, but again, if you double the price of steel, you increase the price of a car by 2%. The finished good is not that much more expensive. This gives us policy options to consider. Same thing with something like methanol. Here again, CCS ends up being useful. It ends up being cheap. It ends up being not so bad. So what are our recommendations? First of all, we got to focus on this. There aren't research programs on industrial heat anywhere in the world. We should be working on this. That's a good thing to do. Second, we need more and better options. CCS is likely to prove important. I'm not satisfied with that. You shouldn't be either. We're going to need better options that are cheaper and more effective. And the last thing is we're going to need lots of policies, including things like government procurement, and they seem kind of effective and they seem actionable today. We need a whole lot more innovation, though. If we think we're going to solve this problem with the tools we have today, we're kidding ourselves. We know that's not true. And we need to work on this a whole lot more if we're going to solve the problem. Thank you for your time and attention.
Thank you, Fabio. Okay, I think we have a little bit of time to have one question to everybody. But in your estimation, which is the real time scale we are facing in our business to have the decarbonization?
For the steel industry, the time aspect is very important because the facilities normally are having an economic lifespan of very, very long. For blast furnace, for example, it's normally 15 years when you make a reinvestment. It will run 24/7 for 15 years. And then you make a stop, and then you make a new investment, you will run another 15 years. For a coke oven plant, which is the blast furnace process is based on, a normal lifetime is around 50 years. So if we really want to achieve the transition, we really need to start now, because otherwise we will be locked in for another 50 years, which will be too late.
Right, I completely agree with that. That's also true for cement kilns. That's also true for petrochemical plants like ethylene crackers. They are very long-lived capital stocks. It's part of the reason why we focused on retrofit or modification of existing plants. Because if you wait until you replace the plants with a new kind of technology, we have real problems. So, and again, hybrid being a notable example, in Sweden, the circumstances on the ground actually favor early replacement. But in fact, that's what you're competing against. You're competing against the tear-down cost of an existing asset, and it's a very high hurdle. I think in terms of the real timeline of this, we're probably gonna have 5 more years of fumbling around while the governments of the world can't figure out how to tie their shoes, and EU tries to figure out how to balance between Spain and Poland, and that's real work and it's a problem. After 5 years, everybody here is gonna be at risk. Everybody here is going to be at risk, and there's going to be some crazy version of carbon border adjustments or people lashing themselves to, dump trucks. There's going to be some crazy extreme action. There's going to be volatility in financial markets. There's going to be questions about assets. The labor unions are going to get into it. It's going to be really, really hard. And in that context, I think we have maybe 5 years to figure out what we want to do, and then we got to execute pretty much right away.
Yes, if I complement this answer, one question is how long it will take for the industrial sector to abate CO2 emissions to a given point that could be useful for the whole picture. because every sector is different. So you go to mobility, of course mobility, we have seen this morning, you can change the landscape of cities in 10 years between the horses and the internal combustion machine. Okay, so mobility, maybe it's easier to reach CO2 abatement faster than industrial facilities that requires investment of decades to be really a return of the investment. So the question is, if this, that we need to do now, because there are even some people that say that the degrees that it will be reached from the point in 90s could be even already like what we have emitting now is 1.3 Celsius. So we have two decimals of error. So that means that we need to start now to do everything, not only in this sector, in all the sectors. Some sectors will do it faster, some sectors will do it slower because of the nature of the processes. It's not the same to change a car than to change a factory. And then I also agree that we have to move now with all the technologies that could be available. Everybody, so all the meat on the load, you know? Not thinking about this is good, this is bad. Look, I have an illness, I'm sick, I take a pill, even if I know that this pill has some effects that maybe are not the good ones that I have at the end, you know?
Yeah, just to add something, I think from the cement point of view, it's true, the same logic, but locally we have different options. We have something that we can start now that's already feasible, like fuel substitution, replacement for wastes, biomass, as I showed, clinker replacement as well, work with better use efficiency in construction. We have a lot of inefficiency, a lot of wastes in the process of construction. We want to work with the whole value chain to bring more efficiency. So this is things that we can start now. And then different technologies that we need for the long term, then we have time like to still to put efforts on that and to have that develop 2030 or so when we really need that.
Okay, I think it's time, so I'll let you to thank all the group of these panelists. Thank you for coming and you for your attention. Thanks.
Thank you. Excellent presentation.